All right, so today we're just going to go over some things about the midterm and some things about the upcoming final as well before we start today's lecture. So the first thing is the multiple choice in the midterm. So the multiple choice in the midterm was actually quite good. There was less than one multiple choice question wrong per exam. So that's very good. And there's really no one multiple choice question that gave people more problems than any other. So that's good as well. So I'm not going to go over any of the specific multiple choice questions. Obviously, if you have a question about one, just send me an email, come to my office hours, just let me know. Okay, then number 5. So the main thing that gave people problems with number 5, this was the Coulomb's law problem, was basically just either breaking the vector up incorrectly or adding it incorrectly, getting like a negative sign wrong somewhere. Sort of those basic kind of problems. So as you have seen as we do magnetism, Coulomb's law is used again in our chapters on magnetism. And if you look at the practice final, there is a question that uses Coulomb's law on the practice final. So you definitely need to know and remember Coulomb's law for the final exam. So if you lost points on this problem, make sure that you know where you lost points so that you can correct that and be aware and not do that on the final because you'll almost definitely need to use Coulomb's law again on the final. Okay, then for the Gauss's law problem, the main mistake that was made was getting the charges here wrong. So I was very happy that almost nobody got the area of the sphere wrong. Everyone had 4 pi r squared, so that was good. But then it was just mainly getting these charges wrong. So if you made a mistake in your charges here and then carried it over to part B, but were otherwise correct in your electric fields, I didn't take off points twice for that. I only just took off points once up here. But if your charges weren't consistent, so if you had one set of charges here and then a totally different set of charges in part B, then I did take off points again because now it's like 2 different mistakes basically. But overall, part B was also very good. Almost everybody got the electric field was 0 inside a conductor. Again, almost everybody, I think everybody used the right 4 pi epsilon naught r squared on the bottom here. And yeah, although I will say almost everybody also forgot their vector signs. I didn't take off for forgetting that, but just be aware you do need to include your vector signs whenever you're doing a vector, obviously. Okay, so part B was pretty good. Part C was like the challenge part of this problem, obviously. So you could do it 2 ways. You could integrate like this. We did a similar problem where we integrated the electric field for a conducting sphere and found that it was constant inside. Or you could just say, I know the potential is constant and I know the potential is continuous. So it has to have whatever value it is on the surface out here, this outer surface, it has to be that same value all the way through that shell. So that was a way to do it without any integration. I don't think anyone said that the potential was 0, given that the electric field was 0, so that's very good. That's normally a very common mistake that people make is they see the electric field is 0 in here and they say, okay, well then the potential is 0, but I don't think a single person made that mistake, so that's good. Okay, so so like I said, the majority of people lost points just on their charges over here. Okay, then for number 7, so this was similar to a homework problem. There was a homework problem. We had a charge moving towards like a nucleus or something. You had to find the distance of closest approach, how close it would get to that target nucleus, and then it would turn back and sort of like go away from the nucleus. So part A, almost everybody got right or, close to right. If you made a little mistake and you forgot a squared here or something, that's fine. But almost everybody got this right. Almost everybody got part B right. At least the closest, the point where the force was the strongest, almost everybody got that right. And almost everybody got this right too. Most of the mistakes were just sort of like algebra mistakes, not really physics mistakes. And then for part C, again, most people got this right, but the most common mistake was this negative sign. So you had to be careful here because it asked for how much work did the electric field do, not how much work did an external force do. So the work done by the force that we're looking at is the negative change in potential energy or the change in kinetic. So you have a negative 0.46 picojoules there, not a positive 46. Okay, but overall, again, this question, everyone did quite well on it. Okay, and then for number 8, this one was a little bit tricky too with the circuit. So there were two basically ways to solve this problem. You could solve this problem by realizing that this resistor and this resistor here were in parallel. So this resistor over here was drawn up here, but there's no difference if that's the only resistor that's in this sort of segment of wire. There's no difference with drawing it here or drawing it here. They're still in parallel. Or you could draw it down here and they're still in parallel. So if you didn't realize that they were in parallel, you could still solve the problem using Kirchhoff's laws. So you didn't need to realize that they were in parallel in order to solve the problem. If you did realize they were in parallel, obviously that simplified things a bit, and you could just jump right to adding up your equivalent resistance in parallel and series. You could find the current through the battery, and then you could find the current down here. Like I said, so there were a couple ways to do this problem. You could not use Kirchhoff's laws at all, or you could do the problem using Kirchhoff's laws, and both ways would get you the right answer. Okay, and then the grade distribution. This is the grade distribution here. So the most common grade was a B plus or A minus. We have pretty much a bell curve. There's a little, like 1 or 2 extra grades in this column, but that's really not unexpected. So like I said, the average was a 72. You aim for something around a 75, so a 72 is well within the expected range. It's a lot of material to learn in 6 weeks, and it's not easy material either. So that being said, the final is a week from Wednesday. So since this is an accelerated course, we already have our final next week. The final will focus on material from chapters 27, 28, and 29, so things after the midterm. However, as you've seen so far with some of the stuff we've been doing for magnetism, you do need some of the material from the earlier chapters. So, like I said, Coulomb's law, we're going to be using again. Some basic capacitors, like just the electric field in a capacitor, we'll be using in chapter 29. Basic circuits, basically just Ohm's law. When we do chapter 29, you'll see we use V equals IR again, but no Kirchhoff's law, no equivalent resistance, no equivalent capacitance, nothing like that. It's really just V equals IR we use again. And yeah, those are the main things that we use in these later chapters. So, but you'll see as we do more problems, you'll see sort of what material keeps coming up from those earlier chapters. Okay, so the final, like I said, will be very similar to the midterm. It's going to be, a couple multiple choice, a couple short answer. You'll have, an hour and 50 minutes. It'll be during lecture time, just like the midterm. And the formula sheet is posted on the exam info page. There's also a practice final under quizzes. The solutions are there as well. So, give that a try once we finish up our material on Wednesday. So this Wednesday, we will finish up all of our new material that will be covered on the final. So that way, we'll finish up our material on Wednesday. You'll have a whole week until the final. We don't have class on Monday because it's Labor Day, so there's no discussion, no lecture. I might have office hours anyway if people want that. I'll definitely have office hours on Tuesday before the exam as well. And we will have a review session on Friday. So I'll do some example problems. I'll do the problems that were planned for Monday's discussion. I'll go over those discussion problems you didn't get to last Wednesday because of the midterm. So I'll just go over a lot of problems, like midterm type problems that you can expect to see. So that's what I'll do on Friday. Okay, so that's really it, I think, for all the information that you need right now for the final. The proctoring will be the same, pretty much same as the midterm, just different material. Okay, so that's really it. So let me know if you have any questions, more specific questions about, final, midterm, anything, and then we'll get started on today's lecture. All right, so now we're going to move on to the second part of chapter 28, which is Ampere's law. So we're just going to do Ampere's law. Basically, that's all we're going to do today. So just a reminder from our previous lecture, we said that the magnetic flux through a closed surface is always zero. So there's no useful Gauss's law in magnetism. Now, Gauss's law is still true in magnetism because if you take the integral of the magnetic field over any closed surface, it will give you zero. It's just not useful for finding the magnetic field like it was in electrostatics. So another way to think about this is that for every single magnetic field we're going to see, the field lines coming into a closed surface are going to be the same as the field lines going out of a closed surface. So if I just draw some random surface right here, I can see that every single field line that goes in to my surface comes back out. And this is the field for a wire. And here, this is like the field for sort of a dipole or a bar magnet or a current loop. The same thing. Anywhere I draw my surface, you can see that the field lines going in are the same number of field lines going out. And that's going to be true no matter what sort of shape I draw, no matter where I draw it, that's going to be the case. So Gauss's law won't help us solve for the magnetic field in the case of magnetostatics. Now, remember that we saw last time, so we saw the magnetic field for a current carrying wire, and we saw that the magnetic field will curl around that wire, right? So if we look here, we're looking at a wire sort of head on, so the wire current is going into the page, and we're going to see a magnetic field curling around it according to the right-hand rule. And we didn't really see anything like this in the case of electrostatics. We never saw an electrostatic field that curled around a charge, and in fact, we said that that could not happen in electrostatics, because if that did happen, it would imply that the electrostatic force was not conservative, and we knew that it was conservative. So what this is going to imply to us here is that now, so remember for electrostatics, we said that the integral of the electric field around any closed path was going to be equal to zero because it was conservative. Right? And we showed in one of our earlier lectures that those imply each other. Now, we can see here that the integral around a closed path in the magnetic field is not going to be zero, because as we trace around this one of these loops here, there's magnetic field in every point of our closed path. So we can see here that the line integral of the magnetic field around a closed path is not going to be zero. And this is our final Maxwell's equation. So our final Maxwell's equation, we can write, as always, in either integral form or differential form. So our final Maxwell's equation can be written like this in integral form. So the integral form here tells us that the line integral of the magnetic field around any closed path is going to be equal to mu naught times the enclosed current that path encloses. Now, obviously, we're going to be using this a lot today, so we'll see how this works. So this sort of looks like Gauss's law. It's a little bit reminiscent of Gauss's law with the enclosed current versus the enclosed charge. But the only difference really is that now we're doing a line integral as opposed to a surface integral. So that's what our fourth Maxwell equation says in integral form. Now, in differential form, it tells us that the magnetic field curls around a current density. So that's all this equation is telling us, is that if we have a current density J, the magnetic field, this is the curl, the magnetic field will simply curl around that current, which we've seen here with our wire loop. So we have a current density right here, right? We have a current going into the page, and very clearly our magnetic field is curling around that current density. All right, so now let's see how to use Ampere's law to solve for the magnetic field. So just a general statement of Ampere's law again. So this is Ampere's law. So just like with Gauss's law for the electric field, we are only going to use this when we have a very high degree of symmetry, and we're going to see the cases where we can use this and where we have enough symmetry that it will make Ampere's law easy for us to use. So again, Ampere's law just states that the magnetic field integrated over a closed path will be equal to mu naught, which is the magnetic constant, times the enclosed current in that path. And it's very important that we use a closed path. We don't want to have just a path like this, like just a line that's open. We want to always have a closed path, like either a circle or a rectangle. I mean, you could technically make, any closed path you want, but you want a path that's easy to integrate around. So we're typically going to be choosing paths like circles or rectangles that are easy. Okay, so let's get sort of a little bit of a conceptual understanding of how this works. So again, it's important to remember that Ampere's law now, we're looking at a 1D integral. It's just a line integral, so that means we're only integrating in like one dimension, as opposed to Gauss's law where we had that dA. So we were really doing an integral over 2 dimensions, over a surface. We were looking at enclosed like volumes basically. Here, we're only looking at a 1D integral. So in the case of Ampere's law, let's say we have 3 current carrying wires here. So we've got I1 and I3 going upwards, and I2 is going in the opposite direction downwards. And if we just draw some arbitrary path around them, like this, the enclosed current sort of enclosed in this little cross section here, this is going to be equal to I1 minus I2 plus I3. So we say that I1 and I3 are positive here because they're going in the positive direction according to the right-hand rule. So if we chose to integrate in the direction here, you can sort of turn your hand in the direction of that line integral. So we curl our hand in this direction. We see that our thumb is pointing upward. So according to our right-hand rule, this is the positive upward direction. You can always use your right-hand rule like that. If you curl your hand in the direction that you're integrating, or the direction of your closed path, your thumb will be pointing in the upward direction. So that's why I1 and I3 get a positive there. So we have plus I1 and plus I3, and then minus I2, since that's going in the downward direction now, according to our right-hand rule. Okay, and then just a reminder, or a little technicality, just like with Gauss's law. So if I have, let's say I have 2 wires here, and I have I1 going in this way and I2 going in this way. Now, if I draw a Amperian loop, we call it, so if I draw an Amperian loop that encircles both of these currents, right, so let's say I integrate this way, and I do B dot dl is equal to mu naught I enclosed. Now my I enclosed in this case is 0 because I have a current going in this direction, and then I have the same current going in the opposite direction. Let's say these are the same magnitudes. So I'm going to have 0 here. But that doesn't necessarily mean that my magnetic field is 0, so this doesn't imply that my magnetic field is 0 in this case. It just means that the line integral of my magnetic field around this path is 0. And just like with Gauss's law, if we want to be able to say, well, the enclosed current in a region is 0, therefore the magnetic field is 0, we need a very, very high degree of symmetry in order to make that argument. So we'll see the cases where we can make that right now. So, okay, so that's just something to keep in mind. In a general scenario, this is not necessarily true. We just, just think back to our last lecture where we calculated the force that these 2 wires exert on each other. So obviously the magnetic field between them is not 0. It's just the line integral of the magnetic field that encloses both of them is 0. Okay, so now we're going to do an example to see when we have a high degree of symmetry, how we can use Ampere's law to find the magnetic field. So we want to use Ampere's law to find the magnetic field a distance r from the axis of a current carrying wire. So this is a case that has a high degree of symmetry. So we have some wire, let's say going like this, and it has some current I going down it. Now again, you're going to have to sort of know what the magnetic field looks like beforehand. So in the case of a wire, you have to know that the magnetic field is going to curl around that wire. That way you know where to draw your Amperian loop. So I know that the magnetic field is going to curl around the wire. So I'm going to draw my Amperian loop around the wire like this. And this Amperian loop has some radius r. So now I can write Ampere's law. So I have B dot dl is equal to mu naught I enclosed. So my B dot dl I can rewrite as just B times the circumference of this loop. So I can just write 2 pi r is equal to mu naught, and then the enclosed current is just I. And the reason I could do that is because I know if I center my Amperian loop just a radius r from my wire, I know that the magnetic field is going to be constant over that loop, because the magnetic field can only depend on the distance from the loop. So if I'm at some fixed distance, little r, my magnetic field will be constant over that integral. So let's just go back to here. So we can see here, so this is an argument by symmetry. The only variable that our magnetic field can depend on is the distance from the wire, since it's symmetric in every other dimension. So if I just draw a, if I just draw a loop over this, this magnetic field line here, I know that the magnetic field is going to be constant over this entire loop because it only depends on the distance from my loop. And since this loop is just a radius r, the magnetic field will be constant over this entire loop. So that's the symmetry argument that we're making with a current carrying wire. So now I can just solve for my magnetic field, and I get B is equal to mu naught I over 2 pi r. And that's it. And that's what we got when we did it the long way with the integral. So here, and then we'll just have to use the right-hand rule to find the direction. So in this case, if our current is going to the right, we just curl our hand, and our hand will be in the direction of the magnetic field. So the magnetic field, in this case, it'll be sort of looping around like this, and it will be coming out of the top of the page. So up here, it will be coming out of the page and then going back in at the bottom down here. All right, so that's obviously much simpler than how we did it the long way with the integral. All right, now let's do a cylindrical conductor. So we can make the exact same symmetry arguments that we just made. So we'll be able to use Ampere's law for a cylindrical conductor as well. So for this case, we have a cylinder, an infinite cylinder that has some width to it now. So it's not an infinitely thin wire. It now has like a radius out to r. So our cylinder is out to radius r. And it carries a current I. So the current is uniformly distributed over the cross-sectional area. So that means I is spread uniformly throughout this. And this is like a cylinder, so it's an infinite cylinder like this. Okay, find the magnetic field as a function of the distance r from the axis of the conductor for points outside and inside. So we want to find the magnetic field everywhere, both inside and outside this conductor. So let's start actually outside. So we're going to be using Ampere's law. So outside the conductor, we can already guess what our answer should be, and it should look like that of an infinite wire. So we should expect basically this. So what we can do is, let me draw this a little bit smaller. So what we're going to do is we're going to have our Amperian loop out here, and our Amperian loop is some radius r. So let's do when r is greater than the radius. So we will have, for our Ampere's law, B. Now B is constant over this Amperian loop by symmetry. So we're just going to multiply it by the circumference of our Amperian loop. It's enclosing a total current of I, because we said this wire carries a total current I. So since it's spread symmetrically over this cylinder, we can just say, okay, the total current enclosed is I, and here's our Ampere's law, and that's it. So then we have just solve for B, and we do get the exact same answer as before. And in this case, let's say if the current was coming out of the page, so let's say our current was sort of flowing in this direction, that would mean that our magnetic field is, according to the right-hand rule, if the current is coming out this way, my magnetic field is curling around like this. So this is how my magnetic field is curling around sort of counterclockwise. Okay, now let's look at inside the conductor. So inside, let's just draw the same picture. All right, so now first of all, where am I going to draw my Amperian loop here? So I'm going to draw my Amperian loop inside the conductor, since that's what we're looking at now. So I'm going to draw an Amperian loop somewhere in here. And my Ampere's law is B dot dl. And I'm looking at points that are less than capital R. So the left-hand side of this I can do relatively easily because I know it's just going to be B times the circumference of my Amperian loop, which is 2 pi r again. So this is still at some radius r here. But now what is my enclosed charge? Well, I'm going to have mu naught for sure. And now my enclosed current, I said that it has a total current I spread uniformly throughout this whole area here. So the current that's in here, I'm going to have to find the current density and then multiply by this area. So remember that the current density is I over the area, the cross-sectional area. So my total current is I. The cross-sectional area is pi r squared. So that's my current density. So my current density is I over pi r squared. So to find out how much current is in this area here, I just have to multiply that density by the area enclosed by this Amperian loop. So my I enclosed is going to be the current density times the area of my loop. So that's going to be I over pi capital R squared times pi little r squared. So make sure you keep your capital R's and little r's sort of separate. This is the density, the current density. So that's going to have a capital R on the bottom because it's the total radius. Whereas this area is going to have the lowercase r because that's just the area that's enclosed by my Amperian loop. So I can see that my pi's cancel and I'm left with just I r squared over capital R. So I'm going to plug that in right here. So I have I little r squared over capital R squared. Now I'm going to divide by 2 pi r from both sides. So I have B is equal to mu naught I little r, and then I have a 2 pi r here. So one of my r's cancels, and I'm left with mu naught I r 2 pi r squared. So this is my magnetic field inside that conductor. And it makes sense that our magnetic field is increasing with R because as we move further and further out in this conductor, we're enclosing more and more current. So it makes sense that our magnetic field should be getting stronger with the radius while we're inside the conductor. And then as soon as we are outside the conductor, it looks like that of an infinite line again. So, and then the direction of this will be the same as in the previous part. The current's coming out this way. That just means that inside my conductor, the magnetic field will still be going counterclockwise according to the right-hand rule. Okay, so that's our cylindrical conductor. Now, if I were to plot this, so just to sort of have a visual, if we were to plot this, so let me just rewrite these magnetic fields again. So B inside, we had mu naught I r over 2 pi r squared, and then outside it just looked like that of a current carrying wire. So if I were to plot these two things, that means that my magnetic field looks like this. So it looks like a straight line before I get to that outer surface. So capital R is here. So it just looks like a straight line. It's increasing with r, little r. So it's just increasing like this. When we get to capital R, so right here, this is going to be mu naught I capital R 2 pi r squared, right? If I plug in capital R when I get out to right here. So we have that there. And then as soon as we now move outside the conductor, it decreases according to 1 over r. So now we can see that unlike the electric field, our magnetic field does stay continuous. It's not smooth, but it is continuous as we go over that surface of the conductor. Whereas if you remember our electric field, we had a discontinuity when we got to the surface of a conductor. For the magnetic field in our class, that's not going to be the case. It's going to be continuous here. Okay, so this is just the plot of our magnetic field versus our radius. So now let's move on to a slightly more complicated cylinder problem. So here it's sort of like a thick shell. So our cylinder has an inner radius B and an outer radius A, and the exact same setup as before, where we have some constant current I that's spread out uniformly over this sort of like donut shape. So we want to find the magnetic field everywhere. So we're going to want to find it in this region here, this region, and this outer region. And remember, this is a cylinder, so we're sort of looking at it like head on, so that it just sort of looks like a donut shape to us. All right, so let's find when r is less than that inner radius first. So this one's going to be easy since we have a very symmetric configuration here. We can, when we write down Ampere's law, our enclosed current, when we're inside here, we're not enclosing any current, right? Because all of our current is spread out here. So this is just 0, and since we're in a symmetric enough configuration to use Ampere's law, we can just say now that the magnetic field is also 0. So our magnetic field is 0 when we're inside that inner radius. Now when we get into this conductor, so now we're going to move into here. So we're between B and A now. So we're going to write down our Ampere's law. So now we're going to draw our Ampere's law somewhere right in here. So right along this dotted line is our Ampere's law. It's at, our Amperian loop. So we're going to draw our Amperian loop right here along this dotted line. So that's at a radius r. So we can write the left-hand side right away. Now we're going to have a mu naught, and now we're going to have to think about what our I enclosed is again. So what is the I enclosed here? Well, we can't do quite as simple as what we did in the previous problem because we have this centerpiece cut out. So what is the current that's just right in there? So now I need to figure out what is the current density in this conductor. So it's going to be a little bit different than in our previous problem, but we still start off with the current divided by the cross-sectional area. But now what is the cross-sectional area of like this donut shape here? Well, it's just going to be the area of like this outer circle, minus the area that's cut away. So the area here is going to be pi a squared minus pi b squared. And that will just give us this area here that's making up that donut portion of the cylinder. So this is our current density. Now, when I want to find the enclosed current, again, I have to multiply the current density by just the area that's enclosed in my Amperian loop now. So that's going to be this area here. So the area that's enclosed by my Amperian loop, so I enclosed is going to be J, which we just found, times the area here, which now is pi r squared minus pi b squared. So we have little r, since we're only going out to the Amperian loop radius. So now this is my I enclosed, so I can plug this form for J right in here, and we can put that all here. So I'm going to have J, which is I over pi a squared minus b squared, and then times pi r squared minus b squared. So I just factored out a pi from each of these to make it a little bit simpler. And now I can divide by 2 pi r to get the magnetic field. So I have mu naught I, this pi and this pi cancel. So I'm left with just a 2 pi r here, but then I have this r squared minus b squared, and then I have this a squared minus b squared. So it looks sort of like our magnetic field of an infinite wire, but we have this extra part here from this missing middle part. All right, so that's our magnetic field for this one. And again, the direction can be found using the right-hand rule. So if our current was coming out of the page, our magnetic field would be going in this direction again, counterclockwise. Okay, so that is the magnetic field inside that conductor. Now let me just add a page and we'll do outside. So outside, oops. So when we're outside the conductor, we know what we expect our magnetic field to look like. So let's erase this stuff. All right, so now we're at r is greater than the radius a, so we're outside our conductor. We're going to draw our Amperian loop out there, pretend that's a circle. We'll write our Ampere's law. All right, so B dot dl will be B 2 pi r. Now our I enclosed will be just I, because we were told that the total current on this wire was I, so we don't have to find J or anything like that. We can just write I. So we're going to have B is equal to mu naught I 2 pi r, and that's our magnetic field. So we expect it to look just like that of an infinite wire once we're outside the conductor. And again, if the current is coming towards us, the magnetic field out here will be going counterclockwise. Okay, so that's the magnetic field for some cylindrical setups. Now let's look at a solenoid. A solenoid is made up of, we saw this last time, it's very tightly wound coils. So we have current going through each of these coils in this direction, to the rightward direction. So our current is like going sort of like this. It's going around this way. And we want to know what's the magnetic field of an infinite solenoid. So pretend this solenoid goes up to infinity and down to infinity. What is the magnetic field of that, that case? So we're going to use Ampere's law for this. And now the way we're going to use Ampere's law for this is we can't draw an Amperian loop or at least an Amperian loop in here won't help us because there's no current enclosed in that. And an Amperian loop out here won't help us because there's no current enclosed in that. So what we're going to do is we're going to draw an Amperian loop sort of right here around the edge. And so let's pick a direction for this. So I'm going to draw an Amperian loop that's sort of like a rectangle that like crosses over the edge of the solenoid. So it goes in on this side here. So this is inside in the interior of the solenoid. It cuts through the edge here, comes outside, and then goes back in. So this loop now has 4 pieces. So there's 4 contributions to our integral. So when I do b dot dl, each one of these sides of my rectangle will contribute, or at least have to be taken into account when we're doing this line integral. So inside the center of a solenoid, an infinite solenoid, our magnetic field is basically constant. So our magnetic field is essentially constant in here. And we want to take a solenoid, we're considering a solenoid that's not too wide. So the radius is rather small. So you can sort of think like, if I drew the magnetic field for each of these individual wires, so let's just look at like one of these wires. I know the magnetic field is going to be curling around each of these wires, right? So on the inside here, my magnetic field, so let me actually redraw that, that's not that good. So let's just get rid of 2 of these. Okay, so if I draw my magnetic field for an individual wire, it's this direction, upward. So let's just, okay. So if I draw the individual magnetic field lines for one of these wires, it sort of looks like this, right? So it's wrapping around this wire. So for this individual wire, according to the right-hand rule, the magnetic field is wrapping around this way, and same for this wire down here, it's wrapping around this way. So inside the solenoid, you can see that my magnetic field is pointing in the same direction for both of these. So the magnetic field actually ends up just being constant when you take into account all of the contributions from every piece of all of these wires here. The magnetic field ends up being constant inside your solenoid. And then outside our solenoid, we can sort of look at it 2 ways. We can say, well, there's no current outside, so B is 0 outside, but that's not the best way to do it. So outside our solenoid, the magnetic field lines out here end up being canceled by the magnetic field lines coming from this side of the solenoid. So you don't really have to worry too much about it. You can just take it as a given, sort of, that the magnetic field outside our solenoid is 0. That's for an infinite solenoid. Now, physically, the magnetic field is just very, very weak outside a solenoid because we can't really have infinite solenoids. But usually when we're doing Ampere's law, we just take it as 0 since we're just sort of doing an approximation. So our magnetic field ends up canceling outside our solenoid, and we only have a constant magnetic field inside our solenoid, an infinite solenoid. So now let's get back to our integral. So we said that in here, so on this little leg of our rectangle, we have B times L. So whatever length this rectangle has some length L, and we know that the magnetic field is constant in this interior, so it's just going to be the magnetic field times the length of this piece of Amperian loop. So this is just B dot L. So we have BL over here. Now over here, our magnetic field is going upward, and again, I'll show you the right-hand rule for a solenoid in a second. So we said that our magnetic field is going upward, but our integral is perpendicular to that. So the dot product will give us a 0. So we have no contribution from this portion of our integral. And then out here, our magnetic field was 0. So we have B equals 0 out here. So when we do B times L, that's obviously just going to be 0. So we have no contribution from that portion either. And then the same thing down here. Our line of integration is perpendicular to the magnetic field, so the dot product will give us 0. So we have another 0, and we're left with just that one contribution from B times L. So now this is going to be equal to mu naught. And now the I enclosed here. So how many or how much current is enclosed in this portion of my solenoid? Well, let's say that typically for solenoids, they'll tell you the amount of turns or coils per unit length, and we call that N. So we have each coil has some current I, and there are small n turns per unit length. So to find the total enclosed current in this section, we just have to do the number of turns per unit length times the length, and then each one has current I, and that will give us the total enclosed charge in this portion. Okay, and then that's it. And then we just solve for B. So just divide by L, and we get mu naught N I, and that's it. L's cancel, and this is all we're left with. And now the direction of this, as I wrote it here, is upward. And the way you can figure that out is, well, I drew it here, first of all, so you could see how the magnetic field gives you an upward direction inside the solenoid. But you can also use the right-hand rule for solenoids. So for solenoids, what you do is you can wrap your hand in the direction of the current, and your thumb will give you the direction of the magnetic field. So very similar to the right-hand rule when we did magnetic dipoles. Just wrap your hand in the direction of the current. The current is going this way, how I drew it, so my magnetic field is pointing upward. And if my current was pointing, if my current was going in the other direction, so if the current instead was going this way, I would have to flip my hand over in order to curl my hand in the direction of the current, and then my thumb would be pointing downward and my magnetic field would be downward. So that's how we do the right-hand rule for solenoids, and this is the magnetic field for a solenoid. Now this, again, is something I would absolutely memorize, so that if on the exam it says something about a solenoid, you can just immediately write down the magnetic field for it. You don't have to think about it. So this is definitely something to memorize, as well as just, these two steps to use Ampere's law for it. All right, now let's move on to our final symmetrical configuration where we're going to be using Ampere's law. So this is called a toroid, and a toroid is basically a solenoid. Let's say if you have a finite solenoid, you just put the two ends, connect the two ends so that it creates like a donut shape out of your solenoid. That's all a toroid is. So you can see here, it sort of just looks like a solenoid that's been, bent in on itself. So for a toroid, we say that it's made up of capital N total turns. So this toroid has N total turns, as opposed to when we did the infinite solenoid, we were looking at the turns per unit length. When we denote the total turns for a toroid, we use capital N. And then each turn is carrying a current I. So for this one, we're going to use Ampere's law. So we're going to have B dot dl is equal to mu naught I enclosed. Now I'm just going to draw this, so like imagine we're looking down on the toroid. So let's say the current here, the way it's drawn from this picture, the current is going in towards the center of the toroid. So when we're looking straight down at it, the current is going in this way. So what I'm going to do is I'm going to draw my Amperian loop around this way in my toroid. And the reason that I did that is because I know that the magnetic field for a toroid is going to be zero, both outside the toroid and in this little center here. Basically for the same reason as the solenoid. If you think of a toroid, like I said, as just a solenoid where you put the two ends together, your magnetic field is still going to be zero outside. So all of your magnetic field will be concentrated just like in the donut portion of the toroid. So I'm going to draw my Amperian loop in here. So I'm going to do B. This is just a circle, so my Amperian loop is just 2 pi r. And now mu naught, and now my enclosed charge here. My enclosed current. So my enclosed current is just going to be the total number of turns times the current on each one. So my enclosed current is just capital N times I, and that's it. And then I just solve for B. So B is mu naught capital N times I over 2 pi r, and that is my magnetic field for a toroid. And this is just inside the toroid. It's 0 outside. And again, we can use the right-hand rule to figure out the direction of the magnetic field. So what you do is take your hand, again, curl it in the direction of the current. So here, like, the current is curling in towards the center of the donut. So you curl your hands in the direction of the current, and your thumb will be pointing in the direction of the magnetic field. So that means that my thumb is pointing in this direction. So that means that my magnetic field is going counterclockwise again. Okay, and then just to recap, so here I just drew, these are our 3 main Ampere's law scenarios that we're going to see. We're going to have an infinite wire or an infinite cylinder or a coaxial cylinder, something with cylindrical symmetry. And then we'll have an Amperian loop that's just a circle that surrounds that wire. Then the other case is a solenoid, where we sort of take this Amperian loop to be a rectangle, and our magnetic field is just constant inside the solenoid, 0 outside. Or we'll have the case of a toroid, where we draw a Amperian loop inside the toroid, and then the magnetic field is 0 everywhere else. And again, we chose these Amperian loops for the same exact reasons how we decided to choose our Gaussian surfaces. We want to make that integral easy. So we want to choose Amperian loops where our integral is either completely parallel with the magnetic field or completely perpendicular, so that cosine in the dot product is just either 0 or 1. Okay, so that's it for Ampere's law. So now I just want to talk a little bit about the relationship between the electric field and magnetic field, and how they're really just the same field viewed from different points of view. So it's very easy in our everyday lives to think of the electric field as one thing and the magnetic field as another, and they're separate and they don't really have anything to do with each other. But that's not really true. They're really the same field, and it depends on your position and your velocity, whether you see an electric field or a magnetic field or some combination of both. So let's just think of like a really easy, simple example. So let's just think of a current carrying wire first. So if I have some current carrying wire, and let's say it has a bunch of electrons in it. So it has a bunch of electrons in it, and they're moving with some velocity down the wire to create a current. Now, if I'm sitting still and I just watch this current go by me, all these electrons are going by me at some velocity v, I know that I'm going to see a magnetic field, right? So I know that I'm going to see a magnetic field that looks like this, because that's what we just solved for, current carrying wire. So I'm going to see a magnetic field. So now what would happen if I started moving with the same velocity as these electrons? So let's say I started walking with the same velocity v. Well, think like when you're in your car, if you're moving with the exact same velocity as the car next to you, it doesn't really look like they're moving, right? You see things around you or standing still, so you know that you're both moving. But if there's nothing else around you and you're moving with the exact same velocity as the thing next to you, there would be no way to tell if you were moving or not. They would look like they're standing still to you. So it's the same way here. If I'm moving with the exact same velocity as the electrons and there's nothing else in the universe, it looks to me like we're both standing still then. So now it looks like both of our velocities is 0, and if the charges aren't moving, there's no magnetic field, and it will look just like an electric field from an infinite line charge, right? Because we're not moving anymore, at least they're not moving to me, they don't look like they're moving to me, so now I just see an electric field. So what looks like a magnetic field when I'm not moving will look like an electric field when I am moving. And vice versa. You could think of any number of situations where sort of an electric field will turn into a magnetic field, and a magnetic field will turn into an electric field, depending on how the observer is moving. Now, this scenario I simplified a lot just to sort of make it a little bit clearer. When I post the notes, I'll link, there's some really good videos about this that go through the full sort of like special relativity of it. And it's really interesting, so I highly recommend, if you're interested, to watch those videos. Okay, so that's all for chapter 28. We'll start chapter 29 next time, and I will see you guys then.